technically, we're finished. We have the E field, EP, but as always, we have a big mess, and we want to try to write it in a way that's a little bit nicer, okay? So one thing you might notice about this is here's the amplitude going down to the spherical wave, here's the oscillating part, this is where the action is here, and you can see KB sine theta is always together here, KB sine theta together here, and K sine theta, almost the whole thing together here. So sort of everything that matters in the diffraction problem is in the wavelength, the width of the slit, and the angle on the screen that you're looking at. Right? Those are really the three critical parameters. So they kind of all go together all the time. So what we're going to do is rewrite this with a new variable, beta, and make beta equal to 1/2 K, 2 pi over the wavelength, B, the width of the slit, sine theta. And for now, sine theta really is the position on the screen. Right? That's the angle at which the light is going to go. It tells you where you end up on the screen. Because these these are all the parameters of the problem, the diffraction problem. Okay? They kind of show up together in the equations. Everything's contained in those. So let's do that. E and P is the field amplitude per unit width over that distance r, the oscillating, the wave part, kr minus omega t. And then we had 1 over jk sine theta. I want to replace that with 1/2 kb sine theta. So we need a b up top. We do have to add a b to be able to put a beta down here. And we also are going to need a 2 to make up for that half. Right? So what was 1 over jk sine theta just became b over 2 beta. The same thing. We're just really substituting that in there. Oh, we also need a j. Because, yeah, there was a j in the bottom. Right, so make it imaginary. Right? And then this part will become e to the j beta. Right, it was j kb sine theta over 2. So we're just multiplying j beta minus e to the minus j beta. Okay. So that substitution, in addition to having all the stuff that happens in one parameter, also makes a very useful expression, because if you think about Euler's formula, you know that sine of anything x equals 1 over, I don't want to get this wrong, 1 over 2j e to the x minus e to the minus x. E to the jx minus e to the minus jx. Right? If you just go apply Euler's formula, you can see that that's true. And what that means is we can replace 2j, all this, with just sine of beta. Right? It simplifies it down to just being sine of beta. So we end up with sine of beta over beta. This b, we actually want to stick right here. Okay? So we get EL times b over r, e to the j kr minus omega t. And then we get sine of beta, so that all turns into over beta. All right. So we wrote it this way because now it breaks into sort of 3 nice little parts, right? This describes the amplitude decay. Right, so this is the field amplitude per unit width, and that's the width. Together they make the entire field amplitude. That'll be useful in a little bit. This reminds us that this is a wave we're dealing with. Right, so this is the wave. This is the oscillating part. And then here, this is the diffraction part. This is how the pattern varies in terms of theta and the wavelength and the width b. So this is sort of the pattern you're going to see on the screen.